Okay, and the last one, linked list, right? Views require adding at one end and removing from the other. So let's analyze it. If we're implementing using a linked list, what do we want to avoid? Well, access at an arbitrary element, because getting to an element not near the front is slow. Crap. This is the problem, right? How do we get around this? Because no matter how you do it, we're going to have to either add at the back or remove from the back, right? But a singly linked list typically only has a head pointer. Now we could add, we could make it a doubly linked list, but now we're going to, increase by a percentage the amount of memory that we need to use. Or we could just make a tail pointer, right? Remember, as long as we can justify it, it doesn't matter. So let's create a tail pointer. And that eliminates the need to iteratively find the last node. But what does this mean for our design? So let's imagine we have head that points to this guy, which points to this guy, which points to nothing. So there's our linked list, head, tail. So where do we put our front? Well, we could put our front back here, right? And our back here. And that's really nice because when you NQ, right, you go boom, and then you nuke this, and you bring this here. And then when you DQ, oh, what's the problem? Well, we're going to nuke this guy, right? But then we need to change our pointer to this, and we can't go backwards. So that means that the only way through is to come through this way and up here. So that's a big O of N process. Let's see if we can avoid that. Let's try this again. Let's try this from the top. Okay. So we're back here, and let's try this. So we'll put our front at the head and our back at the tail. Okay. Now, when we DQ, that's pretty easy, right? Now we can do that, and we can just nuke that, and our head comes here. And when we NQ, hey, look at this, right? We can hit that, create our new node, point our old tail to this, point our new tail to that, and change our tail pointer to point to our new tail node. So that's convenient. Our front is at our head, and our back is at our tail. So let's do that. And now it becomes easy, like you just saw. NQing is adding behind the tail node, updating the tail node, and incrementing to our count variable. DQing is removing the head node, returning the element inside after decrementing a count variable, and looking at the front of the queue is just accessing the element at the head of the node, at the head of the list. Right? All of these are big O of 1 operations, but they eat up more memory than arrays, just like before, right? The memory consumption is not changed by its usage. It's just what it is. But like before, we can take a look at the code. We're going to have to import our node. We need a head, we need a tail, we need a length, okay? Our length is our length. That's easy. The first looks just like before, except we're just going to get the head.get element, right? If it's empty, we raise an exception. Otherwise, we get the element, okay? Now let's look at the two interesting cases. We'll look at NQ and DQ. So this is the basic case, right? Hey, create a new tail node with the new element and update the tail. Hey, self.tail.setNext equals node with new element. All right, we're going to say whatever our tail is, set the next. And if you are uncomfortable with this, right, we can just say we're going to create a new node that we'll call new tail. And we'll set our tails next to that new tail. And then we'll just update our tail reference to tail.getNext. These are the same thing, right? So that's why I'm doing it this way, but either one is an option. Why do I have this up here? Well, think about it. If we don't have anything in our list, our head and our tail are none. So we need to make sure that they refer to the same thing. So this is how we can do it in one line of code. We can say, hey, our head node equals our tail node, which equals this new node. That will set these two things equal to this same thing. If you don't like that nomenclature, if you don't like that syntax, you can do this. Same thing, right? Set our tail equal to the new node, set our head equal to the tail, or set our head equal to the new node, set our tail equal to the head. I don't care, right? But that's why we have to do this. We have to make sure that both the pointers point at the right things, right? So think about it this way. We enqueue once, we set them both to the same thing. We enqueue again, now we just move the tail. And then whenever we're done, we increment the length. DQ, we get our first node, we find our head, and we set it to whatever's after the head. We decrement our length, and then we have this weird condition. This is going to do the opposite of what we did here. Hey, when we decrement our length, if we hit 0, if our list is now empty, we're going to overwrite our tail node to none because we don't have a tail node. If we do have an element in there, then our tail node's going to be correct. So we keep rocking. And then we return our value. Again, straightforward. No benefit of this in performance over anything else that is significant. The difference just comes to what you need out of your queue implementation.